Hi, I'm Farrokh Labib, and this talk is based on joint work with Jop Briet, who also happens to be my supervisor. I will first explain the background and motivation behind our work. This is a connection between locally decodable codes and Szemerédi's theorem with random differences. And I will explain how objects called dual functions play a role in this. And these dual functions is the main object that we study in this work. So first, what is a locally decodable code? A locally decodable code encodes a message, an m-bit message A, into a longer code word, like any code. And most often these code words can be seen as some kind of function between an abelian group and plus minus 1. Think of G being equal to Z mod n or FPN, finite vector spaces. And this locally decodable codes have this special property that even after partial corruption, we can still retrieve a single message bit by only querying in a few coordinates of the code word. So in this case, we're only querying at 2 positions of the code word, and with high probability we can retrieve some message bit. And of particular interest in these codes are the code word length, so the length of the code word here, and the message length m, when the query complexity, so the number of probed code word symbols, is a constant, in this case 2. Some examples of locally decodable codes are the Hadamard codes. These are 2 query locally decodable codes of length exponential in the message length. And the Reed-Muller codes generalize this to more queries. These are Q query LDCs of length exponential in the message length to the power 1 over Q minus 1. For a long time, this has been the best LDCs, and in breakthrough work by Yuchanin and Efremenko, they show that they can find much better rates for 3 query codes. So more precisely, Yuchanin constructs 3 query locally decodable codes of length exponential in m to the power the number of message bits to the power 1 over t. And he uses things called matching vectors in FPN for some prime p that is a Mersenne prime. And that's the t here corresponds to this t here. And this is much better than the Reed-Muller codes for 3 queries, because the largest Mersenne prime as of now has t at least 77 million. So we have here LDCs that have length exponential in m over 1 over 77 million, while here in the Reed-Muller codes we have m square root m in the exponent. I will explain later what these matching factors are and how they play a role in our work. And Efremenko later shows that you can even do better. Namely, you can get sub-exponential length LDCs using matching vectors in Z mod L, powers of Z mod L with L composite instead of primes. And the probabilistic method has not yet beaten explicit constructions like these, in contrast with expander graphs. So, so there has been some work on this constructing good LDCs using the probabilistic method. And one framework is by Briet, Devere, and Gopi, where they give a characterization of local decodable codes in terms of certain probability distributions over Boolean functions. I'm not gonna go into that, but a special instance of their framework uses Szemerédi's theorem with random differences. And I will, so I haven't explained yet what Szemerédi's theorem with random difference is, but they allow, they show, you can use the Szemerédi's theorem with random differences to show existence of certain locally decodable codes. So let me go into what this Szemerédi's theorem with random differences is. So first, what is Szemerédi's theorem? I will explain it first graphically. So suppose you have a wheel with a lot of spokes and you remove 99% of them. So the spokes here that are left are 1% of the total number of spokes. And Szemerédi's theorem roughly says that if the number of spokes is very, very large, and so even if you remove 99% of them, the remaining spokes still contain some kind of structure. And the structure is that of spokes that have equal distance between consecutive spokes. So there is some subset of spokes, the red ones in this case, that have the property that consecutive spokes have equal distance. So that is Szemerédi's theorem. But more precisely, what it says is that any subset A of the integers 1 up to n, think of n very large, the number of spokes, with the number of elements in the subset being a positive fraction of the total number. So think of 1% of the total number of elements. This subset then necessarily contains a non-trivial k-term arithmetic progression. An arithmetic progression is simply a sequence of elements in A of the form x plus d, x plus 2d, all the way to x plus k minus 1d. So there are k terms, and the distance between consecutive elements is d. And this is true when n is sufficiently large, depending on delta and k. So this some terminology, this x here is the starting point of the arithmetic progression, and this d is the common difference. Now we can ask for a more refined version of this theorem, namely, what if we restrict this common difference d to be inside certain sets? This has been studied already, and examples for k large, for any k larger than 1 are, of course, Szemerédi's theorem. So this common difference in this theorem must be inside 1 up to n. Bergersen and Leibman proved that the squares also satisfy this property, that any subset A that has a positive fraction of all the elements of 1 up to n contains a non-trivial k-term progression where the common difference d inside this progression is a square. Also, Woolley and Ziegler proved that for the shifted primes, this property holds as well. Then Franzikakis, Lesage, and Wierdel asked, are these sets special, or has a random sparse set this property as well? So more precisely, this is the problem of Szemerédi's theorem with random differences. And it asks for the smallest row k, for which a Bernoulli row k random set D of G, G is any abelian group or the integers 1 up to n, has a property that Szemerédi's theorem with random that Szemerédi's theorem holds with common difference inside D with probability at least 1/2. So here, Bernoulli Roque random set is just a set that where we pick elements from G independently from each other with probability rho k. And some upper bounds on what this rho k might be is that for k is 2, for any group G, think of G cyclic group mod n or a vector space of I fields. These upper bounds work for all of them. So for case 2, we have log n by n as an upper bound. For 3-term progressions, Christ and Francis Lesage and Wirel prove that 1 over row 3 must be at most 1 over root n. And for 4-term progressions, Briet and Gopi show that similar upper bound holds as well. And the best lower bounds for the cyclic group Z mod n, there is a lower bound by Francis Lesage and Wirel for any k that rho k must be at least log n divided by n. But for vector spaces over finite fields, is somewhat different. Altman proved that it is at least for row 3 n squared by 3 to the power n. So the n square here would correspond to log n square here. And for in general, for any k, Briet proved that for p larger than k, that rho k for fpn must be at least n to the power k minus 1 divided by pn. So again, that would correspond to log n to the power k minus 1. So now let's see how these lower bounds are actually relevant for local decodable codes. So as I mentioned earlier, there's this probabilistic framework by Briet, De Vere, and Gopi that connect Szemerédi's theorem with random differences with constructions of local decodable codes through the probabilistic method. And what they show more precisely is that there exists k-query local decodable codes with message length rho k g times n, at least rho k g times n, and code word length on, where n is the size of the group. And that would mean that having good lower bounds on rho k of some group, think Z mod n or vector space or finite field, that would mean that we get better codes, namely the message length becomes large and the code word length stays the same. So, so relevant to this is a conjecture made by Francis, Lesage, and Wirel that over Z mod n, this rho k probability is at most log n divided by n. And the truth of this conjecture would imply that Szemerédi's theorem with random differences cannot give better local decodable codes than the Hadamard code over this group. And similarly, it is expected, but not explicitly stated as a conjecture, that rho k of fpn is also at most n to the power k minus 1 divided by p to the power n, corresponding to this lower bound given here. Again, if this happens to be true, Szemerédi's theorem in its framework with random differences cannot give better local decodable codes than the Reed-Muller code over this group fpn. So let me state this conjecture again. So in this work, we study the motivation behind this expectation or slash conjecture. So this has been motivated by a conjecture in higher order Fourier analysis, namely a natural finite field analog of a conjecture made by Frantzikakis. And not imprecisely, this conjecture says that dual functions, which I haven't defined yet, can be approximated arbitrarily closely in L infinity norm by low degree polynomial phase functions. I will define all these terms later, but the relevance to this above expectation is that the second conjecture implies the first conjecture. And it is this second conjecture that we disprove. So let me get into the details of dual functions. And I'll start with an example, arithmetic progression dual functions. So a 3AP, standing for arithmetic progression dual function, is a function from a group G to the unit disk D. We can define such functions for any group G, but in this talk, I will be mainly focusing on vector spaces over finite fields. So take G to be Fpn. And it is a function of the form taking D and evaluating it at 3 functions in arithmetic progression. So it's an expectation over all x of f of x times g of x plus d times h of x plus d for some functions f, g, h. So as an example, if you take a subset a of g and let f, g, and h be equal to the indicator function of a, so then you can see that phi of d equals the number of 3-term arithmetic progressions in A with common difference equal to d, then divided by the size of the group. And more generally, an order k dual function phi is given by a pattern, some integer factor of length k, and it is a function of the form given by some functions f1 up to fk, and we evaluate the functions at x plus I1 times d all the way to x plus ik d, and we take the product of them. And as an example, 3APs, 3AP arithmetic, 3AP dual functions correspond to the pattern 0, 1, 2. So of interest are decompositions of these dual functions in terms of simpler functions. And in this case, these simpler functions are polynomial phase functions. We will get into the details now. But first, we look at decompositions of order 2 dual functions. So here the pattern consists of two integers, positive integers I1, I2, and 2 functions f and g. And they can always be written in terms of characters. So these are the Fourier coefficients. But since this function phi has a special form, this decomposition has a property that L1 norm of the Fourier coefficients is at most 1. And this follows by Fourier inversion on f and g. And since it's some kind of convolution, this product, we get that the Fourier coefficients of a chi here are become a product of the Fourier coefficients of f and g, and then you can apply Cauchy-Schwarz to get this statement here. But does this also work for order 3 dual functions using the characters? This happens to be not the case for order 3 dual functions. And an example is as follows. We take the abelian group to be F3n, and our functions are as follows. Here omega is cube root of unity. Then what happens if you evaluate them at a 3-term arithmetic progression, the dependence on x disappears, and phi of d becomes omega to the power d inner product d with itself. Then you can see that the L1 norm of alpha becomes 3 to the power n over 2, because phi d is a band function. All of its Fourier coefficients are have the same magnitude. So by Parsifal, the L1 norm of alpha must be 3 to the power n over 2, which is not really what we want. We wanted the L1 norm to be bounded. So this certainly doesn't work if we only use characters in this decomposition. But what can be done is decompositions in terms of more general functions instead of just only allowing characters. So the following proposition is due to Gowers, and he showed that for any k larger than 2 and any epsilon bigger than 0, or k-dual functions can be written as a linear combination alpha I psi I plus some error term tau, where the psi i's are polynomial faces of the degree at most k minus 1. And a polynomial faces is simply given by psi x, which is equal to a p-th root of unity omega to the power p of x, where p is some polynomial of degree at most k minus 1 in n variables over fp. And what about the error term? Or first, what about the L1 norm of the coefficients? This is the desired thing, that the L1 norm of alpha is bounded, but there are some suppressed constants in there, depending on k and epsilon. And then the error function tau, which is necessary and has the property that on average tau is small. So the capital L1 norm is at most epsilon. So some examples in the previous slide, we saw that order 2 dual functions can be written in terms of characters. So phi is equal to alpha chi times chi, with the L1 norm of alpha being at most 1. But for 3 AP dual functions, we couldn't do it. But what we can do using this proposition is that for this 3 AP dual function phi, we can write it as a linear combination alpha I omega to the power pi, where pi's are polynomials of degree at most 2, and the error term tau, which has a property that the average is at most epsilon. So this proposition has already applications in additive combinatorics, but in certain cases we need more strict control on this tau. So this proposition gives us that the average of tau is small, but in some cases we need that the error is everywhere small, so that the L infinity norm of tau is at most epsilon. And the main question that we try to answer is, does this proposition, this decomposition theorem, hold with tau having L infinity norm at most epsilon? And we show that in fact this is false. We cannot do this in general. So what does this have to do again with Szemerédi's theorem with random differences and locally decodable codes? Namely that if the answer to this question was a yes, so we could approximate any order k dual function arbitrarily closely in L infinity distance using polynomial phases only of low degree, then the given lower bounds on Szemerédi's theorem with random differences over Z mod n and Fpn are all optimal, and that would mean using the probabilistic framework of Briet, de Veer, and Gopi, that Szemerédi's theorem with random differences cannot give better locally decodable codes than Hadamard code and the Reed-Muller codes. So our main result is the following, that for infinitely many primes P, there's a K depending on P, and a set of or K dual functions over Fpn that cannot be approximated in all infinity distance by polynomial phases of degree at most K minus 1. So now we will go through a proof sketch of our main result. Let me restate it again. So for infinitely many primes P, there's a K depending on P such that there's a set of or K dual functions over Fpn. It cannot be approximated in infinity distance by polynomial phases of degree at most K minus 1. And a key lemma that we use here, that we prove, is that for infinitely many primes P, there's a K and pattern I, which we use to define our dual functions, and a set of vectors that has size at least a small omega of n to the power K minus 1, such that a high dimensional hypercube of dimension the size of the set of vectors is inside our or K dual function for this specific pattern I, if we restrict to the set of vectors D. And and there's the fact that there are at most p to the power n to the K minus 1 polynomial phases of degree at most K minus 1 over Fpn asymptotically. And to finish off the proof, we combine the key lemma and this fact, and using some tools from geometric functional analysis to conclude that these polynomial phases, the set of polynomial phases is not enough to approximate dual functions for this specific pattern in all infinity distance. I will not go into this into these tools, but only prove this key lemma, which is the most interesting one. To prove this, we use this result by Ghanen, his construction of matching vector codes. He shows that for prime P and T equal to the order of 2 mod P, there are omega n to the power T orthogonal pairs Ui Vi, such that inner product between Ui Vj is a power of 2 for I not equal to j, and 0 if I is j. So let gamma be a primitive root or a generator in F2 to the T star, and P is a P which is equal to 2 to the T minus 1 is a Mersenne prime. And gamma, so gamma is order P. So the proof which I'm showing now is only for the case Mersenne primes. And because in this case, the proof becomes much cleaner. So then there's a D larger than T, such that 1 plus gamma to the power D is equal to 0. So such a degree exists because gamma is a generator. So then the polynomial p lambda, which is equal to 1 plus lambda to the power D, satisfies p1 is 1 and p gamma is 0. And now if we use these matching vectors ui vj, then you can see that p of evaluated gamma to the power ui inner product vj is 1 if I is 0, if I is 1, and 0 if I is not equal to j. So then for a binary vector A of length equal to the size of this set of orthogonal pairs, so at least n to the power t, and some additive character chi. We define these functions from FPN to the unit disk, complex unit disk, which is equal to chi of sum over j, aj, gamma to the power x inner product vj. We're going to use these functions and this polynomial p lambda to define our dual functions. So we use the property that chi is a homomorphism to evaluate this product. So if you work it out, using additivity of chi, you get this. And then you can pull out one factor of gamma to the power x, vj, and note that this is equal to the polynomial p evaluated in gamma to the power ui vj. And then using the property of p, we can show that, as I noted earlier, that this is equal to 0 if I is not equal to j, and 1 if I is equal to j. So this is equal to chi evaluated ai times gamma to the power x, vi. Hence, if we want to, so a dual function is a really product of a triple of functions, and then you have to evaluate, you have to take an expectation over all x. So taking an expectation over all x, we see that it equals 1 if ai is 0, and minus 1 over p if ai is 1, since gamma is a generator. Hence, since this vector a had length at least omega n to the power t, this dual function of the pattern 0, 1, d, which you can read off from this expression here, contains a high dimensional hypercube, namely of dimension at least omega n to the power t. This finishes off the proof for the case that the prime p is a Mersenne prime. And of course, you need some extra tools to prove this, to prove that we have counterexamples for infinitely many primes p, but I will not go into that. Some open problems. So the patterns, the one that corresponds to Mersenne primes is not an example, a counterexample for 3 AP dual functions over F3n, and the proof that works for that where we show that there are infinitely many primes p for which there exist dual functions that give counterexamples, and those we don't have good control over the pattern. We just show that such patterns exist, but it would be nice to have specific examples for 3 AP dual functions over F3n. Moreover, we only show that there are infinitely many primes, but not, we don't have an idea of which primes exactly, and it would be even better if we had a statement like there exists some p0, prime p0, such that for any prime p larger than this p0, we have counterexamples. Of course, the theorem, Szemerédi's theorem with random differences is still an open question. So thanks.